Alright, we're going to continue on with our circuit elements, kind of building some things up here. We're going to talk, now that we've talked about power supplies, we can actually talk about our first circuit element called a resistor. And we're going to be spending the first several weeks just dealing with circuits with only resistors. And we will add in capacitors and inductors later on. But we're going to first, of course, use something called Ohm's law, which is critical to this circuit analysis. Ohm's law is just so important. And so we'll talk about that, and then we'll revisit power, because Ohm's law is going to allow us a different way of computing power for a resistor. So first off, a resistor is a circuit element that resists the flow of electricity and also flow of charge. So what this means is the higher the resistance, the lower the current. Because if it's resisting the flow of charge, remember, that's actually just our definition of current. And so you might say, well, why do I want something to resist the flow of charge? Well, first off, that doesn't necessarily mean the sole purpose of a resistor. It's just that's where the kind of the name comes from. Resistors have a lot of other applications, really. In fact, their primary application is not to resist the flow of charge. That's just how they were initially, quote, I would say, discovered, and that's what the name came from. So a resistor has a circuit element that looks like this, and then there's some value R, and of course R is just, this is what we call my resistance, and we've already talked about the units of this, and the units of this are ohms. So what should we do here? Well, let's first off know that some typical values are, ohms, kilo ohms are typical values of it. Now, we do get some mega ohm resistors. Much above mega ohm, you don't really see as far as an actual discrete component, but you also will find resistors as small as, you can find resistors of value 0.05 ohms. And you might think for a second that seems silly to even have a resistor of 0.05 ohms, because if you've dealt with resistors at all, you know that that's almost like the resistance of a wire in some sense. But oftentimes when you have values that small, the application for these are often for current measurement. To be able to have a circuit element or a chip be able to measure the current, like a battery charger chip often has a very small resistor as part of its circuit diagram. Okay, so let's get back here to this circuit element R here. So if we have here, again, a convention here, we'll call this voltage here, I'll call it V sub R, because it's the voltage across the resistor. And then I will have a current going through, and keeping to convention here, I'll have the current going into the positive end here. I'll call this I sub R. Now, Ohm's law, we're just going to dive right in here. Was a very important discovery, and its discovery basically relates voltage in mean by that? Well, let's look at the equation here. This is it. That the voltage across a resistor, VR, is equal to the resistance, R, times the current going through it, I sub R. Now, we often will drop the R's in this case and just write this as V is equal to R times I. That's Ohm's law. Now, there is other ways, of course, you can write this. If you simply divide both sides by R, you could write this as V over R is equal to I and get what the current is. So there's lots of ways you can rewrite this, and in fact you could also rewrite it as if you divide both sides by I, you can get that R is equal to voltage over current, which actually is interesting because we can then see that 1 ohm is equal to 1 volt divided by 1 amp is what 1 ohm is. So we can kind of see that just from this equation right here. Now, this is something that some people find useful. I never did this when I learned electronics, but some people find it useful. This little way to remember Ohm's law is they just draw this little triangle here like this. And then what they do in the top here is they put a V, and then they put R, and then I. And so the way they look at this is that you can see that, well, if you have V over R, for instance, that's equal to I. Or if you have V over I, that's equal to R. Or if you circle two other elements here, R times I is equal to V. Now, as I said, I don't find that particularly useful personally. I just memorized Ohm's law here because it's not difficult to memorize, and then just got everything from that. So let's look at a quick example here. So a resistor, let's see here, let's do a 2.2 kilo ohm resistor. Now you might say, why did I choose 2.2? And that's because it is actually a standard value for a resistor. You can technically get resistors in almost any value size, but there are what are some standard kind of values of resistors or groups of values that are fairly common to be used. And a 2.2 k ohm resistor is a fairly common resistor value. So we have a 2.2 k ohm resistor that has 5 volts across it. What is the current going through it? And well, you don't really need to draw a circuit diagram for this, but I'll go ahead and draw what we have here. So we've got a resistor here, and this resistor is 2.2 kilo ohms. And I've got 5 volts across this resistor, and we want to know what the current through this resistor is. Now this is not supposed to be a challenging or tricky question at all. This is just a very basic Ohm's law question. And so what we get here is we get that V is equal to R times I. So you have 5 volts is equal to 2.2 kilo ohms times I. Well, then I is simply 5 volts divided by 2.2 kilo ohms. And again, making sure that you're using kilo ohms as a notation here. When you do 5 divided by 2.2 kilo ohms, we wind up with approximately 2.72 milliamps of current. And it's important that you make sure you get your units right. And again, because 2.2 kilo ohms is the same thing as 2,200 ohms. So when you're doing this arithmetic, it's actually 5 volts divided by 2,200 ohms. You have to always make sure to use that scientific notation. You'll get used to it where if you see, hey, if I'm doing volts divided by kilo ohms, that you're always going to get milliamps. And the reason you can think of that is that if you think about this, is you have a base unit divided by a times 10 to the third. Well, that's going to be a base times 10 to the negative 3. And times 10 to the negative 3 is milli. Alright, but there's not really supposed to be anything complicated. If you don't like this over here, what I just said, I wouldn't worry about it too much. Just do the computation using your calculator. Alright, the last thing we want to talk about is we want to revisit power. Now, the first thing I want to emphasize here is resistors can only absorb power. You cannot generate power from a resistor, so they can only absorb power. Now, we know that my power equation, and we could have computed power in the previous problem, is just voltage times current. It's the same thing as current times voltage, but I'll just write it as voltage times current. But then if we're talking about, and this is emphasize this here, power for a resistor, well, if we're doing that, we can see that, well, Ohm's law tells me voltage is equal to resistance times current. So what am I going to do here? I'm going to take this equation and substitute it up here. So again, I want to emphasize this is for a resistor only. This does not work for voltage sources. It's just for a resistor. Then that power is equal to, well, we would have my resistance times my current, substituting in, times another current, which is R times I squared, which I often write as I squared R. Doesn't matter which way you write it. Doing a similar substitution, we can get power is also equal to voltage squared divided by resistance. So for a resistor, power, we actually have three equations we could use. Voltage times current, which is equal to I squared R, which is equal to V squared over R. And you can also see from these equations why resistors always absorb power. V squared, this is always going to be a positive number. Same thing with I squared. And then R is always positive. So there's no way that the power can be negative. So that means resistors always absorb power. So let's look at one more example here. A simple example with Ohm's law. Okay, so resistor of value 470 ohms has 3 milliamps of current going through it. What is the power being absorbed? Now, again, it's not really necessary to draw any kind of circuit diagram for this, but I like to get in the habit of doing it. And so we've got 470 ohm resistor, we've got 3 milliamps of current going through it, and if we wanted to emphasize the voltage here would be plus minus V. Now, there's more than one way to do problems like this. The simplest, what I would consider shortest way, is again for resistors. Remember, we have three power formulas. One of them is I squared times R, which if we did I squared times R, this would be 3 milliamps squared times 470 ohms. And again, making sure you're careful with all of your units. If you do these computations, and I just did them straight in my calculator, you'd wind up with 4.23 milliwatts. And again, our power is always absorbed for the resistor. Now, that's kind of the quick, short way that I would probably have done this problem. Now, that doesn't mean it's the only way. We could have instead here say, well, wait, I could figure out what this voltage is. We could find V. Using Ohm's law, we get that V is equal to resistance times my current, 470 ohms, times 3 milliamps. And we would have gotten 1.41 volts for this voltage. And then we could say, well, wait, power then we know is voltage times current. And so power is 1.41 volts times 3 milliamps. And of course, if we do that computation, we get the exact same answer as 4.23 milliwatts. Now, the reason I do this in this video here is to emphasize that often when we're looking at circuits or we're examining things, measuring things, there's often more than one way to do these problems. And what's the best way? Well, quite frankly, the best way is the way that you remember how to do the problem. It's not that, oh, this here is the best way that we did here. It's technically the shortest number of computations, but it's not like doing it this way was like took a ton extra time. So there's often more than one way to do these problems. So keep that in mind when you're looking at the problems on the homework. So we're going to end the video here. The next lessons here, we're going to be moving into some more advanced circuit analysis techniques with something called Kirchhoff's current law and Kirchhoff's voltage law, and we're going to learn something about what's called a node and a loop to actually really start getting into some of our circuit stuff.